Hey everyone, it's Mr. Canfield. Today we're looking at 7.2, similarity transformations. All right. So we're gonna do this. Let me read. Let's start with a dilation about the origin with a scale factor of 1/2. Okay, so here's our origin. We're doing a scale factor of 1/2. So I did 2, 4, so half of that is 1 and 2. So go over 1 up to -2, 8. Half of that is -1 and +4. And then 0, 10. Half of that is 0 still and 5. So that would be our dilation with a scale factor of 1/2. And I'm actually going to do a little color code here. Dilate with a scale factor of 1/2. All right. So now it's time for me to change colors, because then let's perform a reflection about the line x equals -3. And I should have said, let's perform that reflection on that dilation. So we have this dilation here. I'm going to draw on a dotted line at -3. And let's make a mirror of this. And here's how simple that can be. How many spaces over is it? It's kind of hard to see because it's a bad copy, but it's 2 spaces over that way, right? So to get there over here, we're going to go 2 spaces over this way. And then I'll go up here. This is 3 spaces over, so we'll go 3 spaces over and put a dot. And then this is 1, 2, 3, 4 spaces over, so we're going to go 4 spaces over here and put a dot. And if I connect the dots, you'll see that we took this and it mirrored itself. So I've taught this a couple of times this year to my classes with these exact packets, and I really don't like how badly the lines showed up. This is pretty frustrating. If you're sitting through this again to hopefully get some more detail, I'm so sorry that you had to deal with the lack of lines the first time through. So anyway, the notation for what we just did to dilate and then reflect is written like this. Notice we see reflect first and then dilate second. That's because this special notation is called composition notation. And it's saying we're going to compose a reflection with the dilation of the triangle. So we're going to make this of the dilation of the triangle. So I need to know what the dilation is before I can do the reflection. You don't need to worry about like the concept of that so much, as long as you get the idea that whenever you see this notation, it's always going to go last, first. And if there's more than one thing, it'll be last, second last, third last, fourth last, or not first, second, third, fourth. Like the first one is always the far right, the last one's always the far left. And yeah, you could do like 10 or 12 in a row. I don't in this class, but you totally could. All right, so for our next one, oh, hold on, go back, Canfield. I didn't color code. So this really should say the line M, about line M, which is x equals -3. Oh, excuse me. Shouldn't have said M, that should have said x equals -3. But we'll see some more like this that I'll have a chance to explain that. All right, so on our next one, it says we want the dilation of the translation of that. So we'll start with this part, T1, -2. All that means is you take each of these points and you move them in the x direction 1, and in the y direction you move them -2. So this point is 3, 5. To move 3, 5, 1 and -2, 3 plus 1 is 4. 5 minus 2 is 3. So 3, 5 is going to turn into 4, 3. Another way to do it is here, I go over 1, down 2. over 1, down 2, over 1, down 2. But, oh my goodness, this printed out so poorly. So this goes to 4, 3. So let me just color code it here, and I'm not going to draw just because it's so bad. So let's see, we have X, Y, Z, and we can put little primes on them. X prime is 4, 3. Y prime, well, this is -1, 4, so +1 is 0, -2 is 2, so 0, 2. And then Z is 1, 7, so +1 is 2, -2 is 5. And now we're going to dilate that by a factor of 2. So one way I could do that is count the spaces and then double the countings, or, wait, I didn't. This is T1, -2. This is D2. Take all these numbers times 2. 8, 6, 0, 4, 4, 10, bam, 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 whoa. And I could plot those points. Depending on what the question is, I can either plot the points or I could just write them down. It really just depends on what kind of question I'm being asked. All right, let's keep going. All right, this one's slightly visible. All right, we're gonna rotate this 90 degrees counterclockwise about the origin. So you can just go like that. And if only it were that easy. It's not that easy. And it's kind of hard to see. But what's going to happen is these 3 dots are going to rotate. And I'm actually going to leave that out of the video because it's not something I'm ever going to test or quiz you on. And when I taught it in class, it just kind of threw people off because they got scared because I was like, hey, here's this thing. Don't worry about it. But they're like, I'm worried about it. So don't worry about that. I will not test you on that. Unless you're seeing this video in honors class and then you need to learn how to do that. Okay. What are the vertices of our axis composed with the dilation of ABC? So let's start with the points. That's -6, 4. B is 3, 5. And C is 2, 1. Okay. So I've got my original points. Which of these do we do first? Yeah, we'll do the dilation first. So we'll take these and we'll multiply the points by 3. So A turns into -18, 12. Here's the thing. If I was going to try to draw that, I don't have enough room on this picture to do it. B will multiply by 3 and we'll get 9 and 15. C multiplied by 3 will get 6, 3. Now that we've done the dilation, let's move on and do the reflection about the x-axis. That's what our x-axis is going to mean. So to do this, well, let's think for a minute. Let's say we have the point 3, 4 up here, and I reflect this about the x-axis. Where is it going to be? It's just a random example. This is a side example. If I have the point 3, 4 up here, if I reflect it about the x-axis and put it here, is it still 3, 4? No. We still went over 3 to get there, but instead of going up 4, now we went down 4. So it's actually going to be 3, -4. So if I want to reflect about the x-axis, I'm going to keep the x's the same, but the y's are going to flip. So -18, -12. 9, -15. 6, 3. Nope, -3. And that's because we're flipping about the x-axis. So if you flip about the x-axis, the y value changes. What would happen if we flipped about the y-axis? So we're here at this 3, 4 thing, and then what if we flip over here? Am I going over 3 to the right anymore? No, now I'm going left to the 3 and up 4. So it's -3, +4. So if I'm flipping the y-axis, the x changes. Whatever one you're changing, X or Y. It's the other letter. That whatever letter you're flipping about, whatever letter you're mirroring about, it's the other letter that changes. So, last question for this one. What transformations were performed to get from here to there, from XYZ to that? So, well, there's some options. One option could be that we rotated it. Another option could be that we dilated it, because sometimes when we dilate, if we use a negative number when we dilate, it'll actually try to turn the thing inside out. So that's why it might have flipped like that. And then there's also a chance, and well, let's talk about how I know it's a dilation. It's definitely a dilation because they're not the exact same size. This one is bigger. And then it's going to be either it's just a single dilation or a dilation and a rotation, or it's going to be a dilation and then a translation moved into it. So I'm curious about this bottom point here. Over 2 up 1, over 4 down 2. So I could see dilating it by a factor of -2, because then instead of going over 2, we go over 4 in the opposite direction. Instead of going up 1, we go down 2. Let's see if that checks out. Over 4 up 1, that'll be over 8 down 2. Oh, I think I found the transformation. And this one over 1 up 4. So then there'll be over 2 in the opposite direction, down 8 in the opposite direction. That's all. That's the whole thing. That's all he did. Anyway, I hope that was helpful, and I'll see you on the next one.